Why isn't the sky blindingly bright? Why is space so dark? When we step outside on a clear night and look up, we see a few hundred bright pinpoints scattered across a vast black canvas. But if the universe is packed with stars in every direction, why doesn't the sky glow like the surface of the sun, or at least like a never-ending city skyline wrapped around the whole horizon? Why isn't the night sky almost blinding? At first glance, this feels like a simple counting problem. There are hundreds of billions of stars in our galaxy, and hundreds of billions of galaxies in the observable universe. If we imagine them spread out more or less evenly, then no matter where we point our gaze, every line of sight should eventually hit a star. Stack enough distant stars on top of one another, and the sky should turn into a continuous wallpaper of light, a glowing shell with no gaps, no darkness, no empty blackness between. Yet that is not what our eyes report. Instead, most of the sky is nothing, black, silent. The stars we see are like a thin dusting of fireflies in what should be a blizzard of light. And this is not just a poetic feeling. Centuries ago, astronomers ran this very argument on paper and realized it leads to a disturbing conclusion. In a universe that is infinite, eternal, and filled uniformly with stars, the night sky cannot be dark. It should be as bright as the surface of a typical star. This means the darkness we actually see is not a trivial detail. It is a direct contradiction. So what is going on? Is our picture of the cosmos wrong, or are our eyes missing something crucial? It should be noted that this single question touches almost every deep idea in modern cosmology. To explain the blackness of space, we have to ask whether the universe is infinite or finite, whether it has existed forever or had a beginning, and whether it simply sits there or expands and evolves with time. In other words, the quiet darkness above your head is secretly an argument about the origin and fate of everything. And here is where things become even stranger. When we point our best telescopes at patches of sky that look completely empty, they explode into view. Hubble's deep fields reveal thousands of distant galaxies where our eyes saw only black. The James Webb Space Telescope pushes even further, uncovering a cosmos blazing with light stretched into infrared wavelengths we cannot see. In the hunt for alien life, we built these instruments to study distant planet systems and their atmospheres, but along the way, they also exposed a deeper truth. So, let's begin. By the end of this video, we will see why the darkness of space is an illusion, why your eyes are lying to you, and how that lie reveals the true story of our universe. So it's time to find out the truth. The paradox of a dark universe. If space is full of stars, why is it so dark? For most of human history, that question was not just poetic, it was a serious scientific problem that refused to go away. Before modern cosmology, many astronomers imagined a very simple universe. It should be noted that in this classical picture, the universe was infinite in size, eternal in age, and static. No overall expansion, no overall collapse. Just a vast, unchanging sea of stars, spread more or less evenly in every direction, stretching on forever. No edge, no beginning, no end. On the surface, that sounds reasonable. After all, when we look up, we do see stars scattered everywhere. But while this picture felt comforting, it hid a terrifying implication. If the universe really is infinite, filled uniformly with stars, then every single line of sight from your eye should eventually hit the surface of a star. Not most lines of sight, every one. This is Olbers' paradox. So let's begin to unpack it carefully. Imagine drawing a straight line from your pupil out into space. If stars go on forever, that line will pass some distance and then intersect a star. If it misses that star, it travels farther, but because the universe is infinite and uniformly filled, it must hit another star later on. Now multiply that by all possible directions your eye can look. The result is shocking. The entire sky should be tiled with overlapping stellar disks, as bright on average as the surface of a typical star. This means that, in an infinite, static, eternal, uniform universe, the night sky should blaze. No gentle constellations on a black canvas, no dark gaps between them, just a blinding, inescapable glare, like standing on the surface of a star that wraps around you in every direction. But that is not what we see. We see a mostly black sky with a few scattered points of light. So it's time to find out the truth. A dark night is not just aesthetically pleasing, it is evidence. It tells us that at least one of those comforting assumptions about the cosmos must be wrong. Either the universe is not infinite, or not eternal, or not static. or not uniformly filled with shining stars. When you stand outside at midnight, it feels peaceful, yet logically, under the old model, it should look almost like a horror movie. No shadows, no refuge, just relentless stellar brightness. In the hunt for alien life, we tend to focus on whether a planet is Earth-like or in the Goldilocks zone, but the very fact that we can see darkness at all is a clue about the entire system of the universe itself. The blackness between the stars is not empty, it is a fingerprint left at the scene of a cosmic crime. In the next part, we will test each assumption of that old infinite universe, one by one, and see which one finally breaks, and what the real culprit behind the darkness turns out to be. How many stars can we actually see? So, if the darkness is a clue, what is it actually telling us about how many stars we can see? It should be noted that this is where we have to stop thinking in terms of the universe as a whole, and start thinking about our tiny illuminated bubble inside it. We live inside what astronomers call the observable universe. That sounds dramatic, but the idea is simple. Light has a speed limit. It has only had 13.8 billion years to travel since the Big Bang. Anything whose light has not had time to reach us yet is, for all practical purposes, invisible. It might be full of stars, planets, even life, but as far as our eyes are concerned, it does not exist. So, let's begin with a puzzle. If light has had 13.8 billion years, should the edge of what we see not be 13.8 billion light years away? This is where the expanding fabric of space steps in. While light has been crossing the cosmos, the space in between has been stretching. Galaxies have been carried away from us like dots on an inflating balloon. This means the galaxies whose first light is only just reaching us now are not 13.8 billion light years away, but closer to 46 billion light years in radius. Around us, there is a cosmic light horizon, a giant sphere about 92 billion light years across. Inside it, every star and galaxy has at least had the chance to send us a photon. Beyond it, no amount of waiting tonight will help. Their light is still on the way. Think of it like standing in a dark ocean at night. You can only see the ships whose lamps have had time to reach your eyes. Maybe there are 1,000 more vessels beyond the mist, blazing with floodlights. But if their beams have not crossed the water yet, your patch of sea stays dark. The universe works the same way. We are surrounded by a finite shell of visible ships in a much larger, perhaps infinite, ocean, and this immediately breaks one of the key assumptions behind Olbers' paradox. The paradox imagines an infinite, eternal, unchanging universe, with stars filling every line of sight. But while the universe might be infinite, our observable bubble is not. We do not see infinitely many stars in every direction, only the ones inside our moving horizon. Optimistically speaking, that sounds like it should solve the problem. Fewer stars, darker sky, mystery over. So it's time to find out the truth. Even inside this finite bubble, there are enough stars and galaxies that the sky could be far brighter than it is. Something else is dimming, stretching, or hiding that light. In the hunt for alien life and for the true structure of the cosmos, we now have to ask a deeper question. What is the universe doing to all that missing starlight? When darkness means the universe had a beginning, what is the universe doing to all that missing starlight? There is one very simple, very radical possibility. Maybe the lights have not been on for very long. In a truly eternal cosmos, with stars shining forever into the past, the rules are brutal. Even if we only cared about a finite bubble of space, every direction you looked would, eventually, line up with a star. Starlight would have had infinite time to travel, to bounce, to overlap. Given long enough, every patch of sky should glow as bright as the surface of a typical star. So why does it not? This is the heart of Olbers' paradox. On paper, an infinite, static, star-filled universe should be blinding. But while the math insists on a sky of fire, our eyes report almost pure darkness. It should be noted that astronomers argued about this for centuries. Dust? Maybe, but dust heats up and re-radiates. Gaps between stars? In an eternal universe, even those gaps are eventually filled by light arriving from farther away. The paradox would not go away. The way out is surprisingly straightforward. If the sky is dark, then the stars have not been shining forever. There simply has not been enough time for their light to accumulate and saturate every line of sight. This means the universe cannot be both eternal and unchanging. Time itself must have a kind of cosmic start date. So, let's begin to call that start date what modern cosmology calls it, the Big Bang. Not an explosion of debris into empty space, but the rapid expansion of space itself from an early state that was unimaginably hot and dense about 13.8 billion years ago. Galaxies, stars, and any habitable planet you can imagine all formed much later, as the expanding universe cooled and structures assembled. Once we give the cosmos a finite age and an evolving history, Olbers' paradox dissolves. Light has a maximum distance it can have traveled since the Big Bang. Beyond that horizon, there can be more galaxies, but their light has not had time to reach us. Even within our observable bubble, many stars have only existed for a fraction of cosmic time. In the hunt for alien life, we often focus on whether a distant world sits in a Goldilocks zone, but here, the entire observable universe is in a kind of temporal Goldilocks zone. Old enough for stars and planets, not old enough for their combined light to fill the sky. Optimistically speaking, the darkness is not a failure of the cosmos to light up. It is a clue that we are living in a young, expanding universe, still in its early chapters, so it's time to find out the truth. This expansion is not just limiting what we see, it is quietly stretching the light itself, turning bright starlight into something that, to human eyes, looks exactly like more darkness. Space is stretching the light out of existence. If the universe is full of light, what happens to all of it as space expands? Because if expansion only pushed galaxies away, the sky should still be glowing. Instead, something stranger is happening to the light itself. To see it, we need to change how we picture the cosmos. Space is not a static stage with galaxies drifting across it. Space is more like rising bread dough, and each galaxy is a raisin. As the dough swells, the raisins move apart, not because they are flying through the dough, but because the dough itself is stretching. This means that over billions of years, the distance between galaxies grows even if they simply sit in place. Now imagine a wave of light leaving some distant galaxy raisin. As it travels, the dough of space stretches. The wave is pulled along with it, so each crest gets farther from the next. The wavelength grows. Blue and ultraviolet light are stretched into red, then into infrared, then into microwave and radio. The photon is still there, but its energy has been drained by the expansion. So let's begin to connect this to the darkness above us. When a very distant galaxy first released its light, it might have been blazing in wavelengths our eyes would consider bright and visible, but that light has had to cross an expanding universe for billions of years. By the time it reaches us, much of it has slipped out of the visible band entirely. To human eyes, it is as if the galaxy dimmed itself and then vanished. Pattern interrupt. What happens if we look with different eyes? Because when we swap our limited vision for a machine like the James Webb Space Telescope, the picture changes dramatically. JWST sees mainly in the infrared, the very wavelengths that expansion has stretched this ancient light into. Point it at a region of sky that looks almost empty through a normal visible light telescope, and suddenly it explodes into view, packed with faint red-shifted galaxies. It should be noted that some of these systems are so far away that their light left when the universe was only a few % of its current age. In the hunt for alien life, we often talk about finding an Earth-like planet in a Goldilocks zone around a calm star. But here, the habitable zone is a band of wavelengths. Our eyes occupy only a tiny strip, and most of the universe's photons have been stretched beyond that strip by cosmic expansion. So it's time to find out the truth about the darkness. Expansion does not destroy light, but it does dilute and stretch it, lowering its energy, spreading it over larger and larger volumes of space. In a static universe with the same stars and galaxies, the night sky would be vastly brighter. Instead, in our real, expanding universe, much of the light has quietly slipped out of sight, leaving the visible sky far darker than the cosmos truly is. Your eyes are lying. The invisible bright universe. So if most of the light has slipped out of the visible range, what are we really looking at when we stare into that apparent blackness? Because space is only dark in the tiny slice of wavelengths our eyes happen to detect. Across the full electromagnetic spectrum, the universe is not a cold void. It is blazing. Our vision is tuned to a narrow rainbow, from deep red to violet, that is all. But while our eyes stop there, light does not. This means every patch of empty sky is actually filled with radiation. Long, lazy radio waves, warm infrared, energetic X-rays, and violent gamma rays. We evolved under one star, so our senses are biased. The cosmos does not share that bias. So, let's begin with one of the most dramatic demonstrations of this. Astronomers pointed the James Webb Space Telescope at a piece of sky so small that, at arm's length, it would be tinier than a grain of sand held between your fingers. To our naked eyes, that exact patch is pure nothing, perfect black, no star, no planet, no faint cloud, just absence. But Webb stared deeper, in infrared light that we cannot see, and suddenly the darkness shattered. The deep field image that emerged is packed with thousands of galaxies, each one a sprawling system of hundreds of billions of stars. Some are so far away that their light left when the universe was young. The same place your eyes call empty is in reality a crowded cosmic city, and Webb is not alone in revealing this hidden brightness. Radio telescopes scan the sky and find it glowing with emissions from cold hydrogen gas, from active galaxies, from the afterglow of the Big Bang itself. X-ray telescopes see a completely different sky again, one stitched together from furious hot gas, spiraling into black holes and colliding galaxy clusters. Gamma-ray observatories map brief, terrifying flashes from stellar explosions and exotic objects we barely understand. It should be noted that, in these wavelengths, the universe is anything but quiet. We can even see this deception in our own Milky Way. In visible light, the band of the galaxy is cut by dark dust lanes, as if someone clawed gaps straight through the stars. But switch to infrared, and those same regions light up. The dust is not empty space. It is absorbing starlight, heating up, and re-emitting that energy at longer wavelengths. The holes in our galaxy are, in fact, glowing, so it's time to find out the truth. In the hunt for alien life, and even just in the hunt for understanding, we have to ask, if the universe is so bright in invisible light, why doesn't all that radiation make our night sky glow like a solid wall of fire to us? And what does that reveal about how energy is really spread out across space, dust, gas, and the cosmic light recycling system? To answer that, we have to admit something slightly unsettling. The universe is not empty, not even the black parts. Between the stars, there is a thin, semi-transparent fog of dust and gas, not just inside galaxies like the Milky Way, but also drifting through the space between galaxies themselves. It should be noted that this fog is incredibly tenuous by Earth standards, yet stretched over light years, it becomes powerful enough to absorb and scatter starlight. So instead of every line of sight ending cleanly on a blazing star, a lot of that light is intercepted, blurred, and dimmed along the way. But where does that energy go? Does the light simply vanish into the dark? It does not. When a photon from a distant star hits a dust grain, that grain warms up by a tiny amount. Then, like a very cold radiator, it re-emits the energy as longer wavelength light, mostly in the infrared. This means the original visible light is effectively recycled into colors our eyes are almost blind to. In the hunt for alien life, we often talk about atmospheres and oceans, but here, the important environment is this cosmic fog, quietly shifting the universe's glow out of our narrow visual window. We can actually see this process at work in our own galaxy. Look at the Milky Way band on a dark night, and you will notice dark rifts slicing through the glow. They look like holes in the star field, as if there are simply no stars there. So, let's begin to reframe that picture. Those rifts are not empty. They are packed with cold dust clouds that block the light of countless background stars. Behind each dark lane, there are more stars, and possibly more Earth-like planets, but their light is hidden, redirected into infrared wavelengths that space telescopes like JWST detect, while our eyes see only darkness. On truly cosmic scales, this absorption and re-emission acts like a vast light-cooling machine. High-energy, sharply focused beams from young stars and hot galaxies are taken in, softened, and re-emitted as cooler, longer wavelength radiation. Spread over immense distances, the intensity of visible light per patch of sky drops. The universe still glows, but more like a lukewarm bath in the infrared than a white-hot wall of visible fire. And even after we account for all this dust and gas, something striking remains. Measurements of the extragalactic background light, the combined glow of all galaxies, show that the sky is still vastly dimmer than the surface of our sun. So it's time to find out the truth. If dust is not enough to brighten the night, what deeper cosmic effects are still draining the visible light from our sky? And what do they tell us about the origin and fate of the entire system we live in? The universe's oldest light is everywhere, and you can't see it. So if dust and distance cannot fully explain the darkness, what is the sky hiding from us? There is a clue, and it is not a distant planet or a single bright star. It is a silent glow that fills the entire universe. Everywhere we look, in every direction, there is an almost perfectly uniform bath of light, not visible light, not even infrared, but microwaves. This is the cosmic microwave background, or CMB, and it is the oldest light we can see, a fossil snapshot from when the universe was only about 380,000 years old. It should be noted that on cosmic timescales, that is practically the first heartbeat after the Big Bang. To understand what this means, we have to rewind to that early era. Back then, the whole universe was a dense, hot plasma of electrons, protons, and photons all tangled together. Light could not travel freely. It was trapped, scattered in every direction like car headlights in a thick fog. Space itself was glowing, but nothing could carry an image or a shadow. Then, as the universe expanded, it cooled. At around 380,000 years, temperatures finally dropped enough for electrons and protons to combine into neutral hydrogen atoms. In that instant, the fog cleared. Photons were suddenly free to travel in straight lines. The entire cosmos lit up in a brilliant, uniform blaze. If we had existed then, every point in the sky would have been dazzling. Here is the pattern interrupt. That light is still here. Those very same photons are still racing past the Earth, through your body, through every star and galaxy. The night is not empty. It is flooded with ancient radiation. But while that glow began in visible and infrared wavelengths, 13.8 billion years of expansion have stretched it. As space itself grew, the waves of light were pulled longer and longer, redshifted out of the visible, then out of the infrared, all the way down into microwaves. Today, the CMB corresponds to a temperature of just 2.7 Kelvin, barely above absolute zero. If our eyes could see microwaves, there would be no dark night at all. The sky would shine with a nearly uniform brightness in every direction, even far from any star. What we casually call black between the constellations is actually filled with this ancient glow, a soft afterimage of a time when the whole universe was brighter than the surface of any habitable Earth-like world in a Goldilocks zone. In the hunt for alien life, we often look for planets and atmospheres, but the CMB tells a deeper story. It confirms that the universe has a finite age and has evolved, neatly resolving the idea of an eternal, static, star-filled system that should be blinding. Yet it also proves that the cosmos was once unimaginably bright everywhere. So let's begin to ask a new question. How did that universal brilliance fade into the patchy, star-studded darkness we see now, and what does that fading light reveal about our ultimate fate, counting all the light in the universe? If the early universe blazed, how bright is all that ancient light today when it finally reaches us? To answer that, we have to literally count every stray photon we can find and ask how much glow is actually spread across the whole sky. Astronomers have a name for this cosmic glow, the extragalactic background light, or EBL. This is not just the light from one galaxy or one bright star. It is the integrated shimmer from every galaxy, every generation of stars, and all the dust that has absorbed and re-radiated their energy across ultraviolet, visible, and infrared wavelengths over the entire history of the universe. In the hunt for alien life, we usually focus on a single planet or a single star system. Here, we zoom out and treat the whole sky as one giant, dimly glowing surface. But how do you measure something so faint that the night sky looks black to our eyes? The trick is that the EBL is not the only glow up there. Closer to home, sunlight scatters off dust in the solar system, creating zodiacal light. Our own atmosphere adds air glow. Individual stars, bright galaxies, even the Milky Way's dust lanes all pile on top. So, let's begin with a kind of cosmic accounting exercise. Telescopes like Hubble and now JWST stare at apparently empty patches of sky for hours or days. Astronomers then painstakingly subtract everything they can identify: foreground stars, known galaxies, scattered light from the telescope itself, even the faint glow of dust in our own system. What is left, after all that subtraction, is a residual haze, the best estimate of the extragalactic background light. It should be noted that this is one of the hardest measurements in observational cosmology. Different methods, from deep galaxy counts to specialized space probes, try to cross-check each other because a tiny error in the foregrounds can mimic or hide the true signal. So what do the data say? In an infinite, static universe, like the one Olbers imagined, every line of sight would end on a star, and the sky would blaze with a surface brightness comparable to the sun. Yet when we add up the real EBL, we get something many orders of magnitude dimmer. If standing next to the sun's surface would be like pressing your face to a roaring bonfire, the actual cosmic glow spread over the whole dome of the sky is more like a single candle flickering miles away. You know it is there, but only with the right instruments. This means the darkness is not an illusion. It is a precise, measurable fact. The universe is finite in age, expanding, and its galaxies are evolving, their light stretched and often hidden from our eyes. Optimistically speaking, that faint EBL is a fossil record of every star that has ever shone. But what if we could peel back more layers of darkness, into wavelengths our eyes can never see, and discover that space is secretly far brighter than the EBL alone suggests? So why does the night look so empty to us? So if the universe is secretly glowing at almost every wavelength, why does the night still feel so empty? We step outside, look up, and what do we see? A few bright stars, maybe a planet or two, and then a vast cold black. But while our everyday experience tells us space is mostly nothing, the data say something very different. When we point our most sensitive telescopes at what looks like a blank patch of sky, no bigger than a grain of sand held at arm's length, thousands of galaxies appear. Each one is a whole star system factory, filled with potential Earth-like worlds and perhaps life. Zoom out, and the entire observable universe is like that, layer upon layer of overlapping light. It should be noted that this hidden brightness is not just invisible starlight. The cosmic microwave background fills all of space with ancient radiation. Interstellar dust grains soak up harsh ultraviolet and visible light from stars and re-emit it in the infrared. High-energy processes near black holes flood the sky with X-rays and gamma rays. If we had eyes that could see all of this at once, the sky would not look empty at all. It would blaze. So why does it not feel that way to us? Why does the darkness between the stars seem so absolute? The answer begins with our own biology. Our eyes are tuned to a very narrow band of wavelengths, the tiny sliver we call visible light. Within that band, they are especially good at spotting compact, relatively bright sources. A star, a planet, a street lamp. We are much worse at noticing extremely faint, diffuse glows that are smeared over large areas of the sky. Think about how you can easily see a single distant car headlight at night, but struggle to notice the soft glow of city light pollution spreading across the whole horizon. The total light in that glow can be enormous, but because it is spread out, it barely registers. The universe works the same way. This means that even if there is a real sea of photons washing over us, our brains report mostly black with a few pinpricks. So it's time to find out the truth about our central question, not why is space dark, in some absolute cosmic sense. Instead, we should be asking, why does space appear dark to human eyes, given how much light is actually out there, and the wavelengths that light prefers to use? That subtle shift is crucial. In the hunt for alien life, we already know that context matters. A planet only makes sense when you understand its star and its broader system. The same is true here. To really answer why the sky looks the way it does, we have to treat our own eyes as part of the experiment. So, let's begin to break the problem into 3 intuitive pieces. How much light the universe actually produces, how that light is spread out in space and across wavelengths, and how our particular biology decides what counts as seeing that light. In the next segments, we will tackle each ingredient in turn, and watch the darkness of the night sky slowly dissolve into something much stranger: brightness, distance, and the dilution of starlight. So if the universe is filled with stars, why doesn't all that light simply add up and bleach the sky white? We've said the darkness is not the whole story, but now we need to see how the light actually thins out. The first ingredient is brutally simple: distance. The brightness of a star falls off with the square of how far away it is. This means if you double the distance, the light you receive drops by a factor of 4. Triple the distance, and it is 9 times dimmer. Push a star 10 times farther away, and you see only 1% of the light per unit area. So even though there are many distant stars, each one contributes an almost vanishing amount of illumination illumination to your patch of sky. But while that law is unforgiving, it would still not save us if stars were packed edge to edge. They are not. It should be noted that even in our own galaxy, the average distance between stars is measured in trillions of kilometers. On the scale of a planetary system, that is astonishingly empty. If the sun were the size of a ping-pong ball, the nearest star would be another ping-pong ball more than 1,000 kilometers away. Most lines of sight simply thread through these huge gaps. The chance that your gaze happens to land exactly on the surface of a distant star is tiny. Our Milky Way itself adds another layer of structure. It is not an infinite fog of light, but a flattened spiral disk with a bright band and dimmer outskirts. In the hunt for alien life, we often picture crowded star fields, but most of the sky does not cross the dense central plane. Instead, your view leaves the thin disk very quickly and then travels through vast intergalactic space, where there are essentially no stars at all. Beyond that, galaxies themselves are discrete islands. Each one holds billions of stars, yet they are separated by millions of light years. From our perspective, other galaxies are so distant that their combined starlight is crushed into extremely faint smudges or an almost featureless glow. It is like standing in a city at night. Nearby streetlights dominate your eyes. You can read a book under them. Far away, on the horizon, the lights of another district merge into a soft, pale haze. The nearby stars and the Milky Way are those streetlights. The ultra-faint integrated glow of distant galaxies is the far skyline, barely lifting the darkness, so it's time to find out the truth hidden in this geometry. When we combine the inverse square law with the real, lumpy distribution of stars and galaxies, the natural outcome is exactly what we see: sharp, bright points scattered on a mostly dark canvas. Optimistically speaking, we have not even used the full physics yet. What happens when we add cosmic expansion, redshift, and the limits of our own eyes? That is where the darkness becomes evidence of something far deeper. If you had supervision, space wouldn't be dark. So what if the problem is not the universe, but our eyes? We keep talking about darkness as if it is a property of space itself. But what happens if we upgrade the observers instead of the cosmos? So, let's begin a quick thought experiment. Imagine we could take our human eyes and push them far beyond their limits. Not just a little more sensitive, but millions of times better at collecting faint light. Then we stretch our vision so we see infrared and microwave wavelengths as easily as we see blue or red. In the hunt for alien life, we often imagine new planets and new stars. Here, we imagine new senses. Walk outside on a clear night with those super eyes. The sky would not be a black background with scattered points. The Milky Way would blaze from horizon to horizon, not as a pale milky stripe, but as a glowing river of structure. Every spiral arm, every dense cluster, every lane of dust would stand out. It should be noted that those dark dust bands we see cutting across the galaxy are only dark to us because they block visible light. In enhanced infrared vision, they would shine, warmed by starlight like embers buried in smoke. Between the familiar bright stars, the empty gaps would no longer be empty. You would see a soft, omnipresent glow from countless unresolved stars and galaxies, plus the infrared afterglow of dust that has absorbed and re-emitted their energy. Instead of isolated jewels on velvet, the whole sky would feel like a continuous tapestry with no truly blank patches at all. Now let's push the upgrade one step further and switch on microwave vision. Suddenly, there is a pattern interrupt. The entire sky snaps into a uniform, gentle brightness. No constellations, no obvious Milky Way, just a smooth bath of light in every direction. This is the cosmic microwave background, the stretched and cooled echo of the hot early universe. In this mode, the idea of a black night would almost stop making sense. Everywhere you look, the cosmos is glowing, but while this supervision would reveal an astonishing amount of hidden light, it would not turn the sky into a second sun. This means the total energy is still limited and spread thin over an enormous volume. Even with every wavelength visible, the night would feel less like a blinding spotlight and more like a dimly lit room, with a constant, gentle illumination instead of a pitch-black void. So it's time to find out the truth about darkness. What we call empty dark space is largely a feature of our biology and our very narrow sensory window, not a true absence of light in the universe. Optimistically speaking, our eyes are telling only a tiny fraction of the story. The rest is still there, waiting in wavelengths we cannot see yet. And once we accept that, a deeper question appears. If the universe is secretly glowing everywhere, why does that hidden light look the way it does? Could the paradox ever come back? If the universe is secretly glowing, could new observations ever reveal that it is much brighter than we think? That is not just a technical detail. It strikes right at the heart of whether Olbers' paradox is truly solved or only temporarily quiet. It should be noted that everything we have said so far rests on our current cosmological model. We rely on measurements of how galaxies recede, on the detailed spectrum of the cosmic microwave background, on distance ladders that tie nearby stars to faraway supernova. This means our explanation lives and dies with that web of data, and as new telescopes come online, that web can be tightened, or in principle, pulled apart. So, let's begin with the most unsettling possibility. Could a future instrument suddenly detect far more background light, especially in the infrared, and show that the sky is actually far brighter than our best estimates? Missions like JWST already probe an incredibly faint infrared glow from distant galaxies. Upcoming projects are trying to measure the extragalactic background light by counting individual galaxies, and also by measuring the total sky brightness directly. What if those two methods refuse to agree in a dramatic way? Astronomers already see small discrepancies. When we add up the light from all the galaxies we can resolve, we get one number. When we measure the smooth glow of the sky and subtract foregrounds from our own solar system and our own galaxy, we sometimes get a slightly higher number. Is that extra light real? Or just dust, zodiacal light, or instrument noise pretending to be deep cosmic signal? In the hunt for alien life, we often talk about how a single weird spectrum from a distant planet might rewrite our understanding of biology, but while that is possible for life, most cosmologists think a similar revolution for Olbers' paradox is very unlikely. The finite age of the universe, the measured rate of expansion, and the exquisitely mapped 2.7 Kelvin glow of the cosmic microwave background leave very little room for a hidden, blinding sea of starlight. Any extra light has to fit within those tight constraints, or it would break the overall system. So it's time to find out the truth about how fragile our solution really is. Right now, teams are working to refine foreground models, launch new infrared surveys, and cross-check every method of weighing the sky's brightness. We are not changing the basic answer, but we are still tuning the dimmer switch. Optimistically speaking, the broad outline is secure. The universe had a beginning, it is expanding, and space is dark to our eyes for deep physical reasons. Yet, an open question remains. How much ultra-faint, diffuse light from the first generations of stars and galaxies is still hiding in that darkness, and what would it reveal about the true history of cosmic starlight, from black sky to Big Bang, what the darkness really tells us? So what does that lingering darkness actually mean? If the universe is full of stars and galaxies, why does almost every direction our eyes look still come up black? To answer that, we had to follow the trail back to a very old puzzle. Olbers' paradox said that if the cosmos were infinite, static, and eternal, with stars spread out more or less evenly, then every line of sight should end on a star. The whole sky would blaze like the surface of a star, not just the tiny patch around the sun. But while that logic is brutally simple, it completely disagrees with what we see every clear night. So it's time to find out the truth hidden in that mismatch. The way out of the paradox is not to deny the stars, but to change the assumptions. This means the universe cannot be both infinite in time and unchanging in space. Instead, our data point to a cosmos with a finite age, about 13.8 billion years. Light has only had that long to travel, so there is a horizon beyond which starlight has not yet reached us. The sky is not the sum of infinitely many stars. It is limited by the age of everything. And the space between those stars is not just sitting there, it is stretching. As the universe expands, light from distant galaxies is redshifted, its waves pulled from energetic ultraviolet and visible into the infrared and even microwave bands. To our eyes, that stretched light fades into darkness, even though in the right wavelengths, it is still very much there. On top of that, the sources themselves are not a smooth, glowing fog. Stars live in galaxies in clusters, with huge cosmic voids between them. Most lines of sight simply do not intersect a star's surface. Dust and gas drift through the structure, absorbing some of the starlight and re-emitting it at longer wavelengths. The result is a universe that, to human vision, looks mostly empty, while in radio, infrared, X-rays, and gamma rays, it quietly shines. It should be noted that our own biology finishes the illusion. Our eyes only sample a tiny Goldilocks zone of wavelengths tuned by evolution to our local star and to survival on one Earth-like planet. We are essentially blind to the microwave glow of the cosmic background and to most of the infrared warmth where that absorbed starlight reappears. What we casually call black space is, in the hunt for alien life, or just in the hunt for truth, more like a dim, omnipresent radiance that our senses filter out. Philosophically, that is a remarkable twist. The simple observation that the night sky is dark becomes evidence that the universe had a beginning, that it expands, that it evolves. The darkness is not a failure of creation, it is a signature of cosmic history. So, let's begin to see that darkness differently, not as empty, but as a signpost, back toward the Big Bang, and outward toward the faintest edges of what we can ever hope to observe. In that blackness, the next section will ask, what else is still hiding from us? Next time you look up, remember what you're not seeing. So let's begin to answer that last question in the most personal way possible. The next time you have a clear night, step outside for a moment. Just stand there. Let your eyes adjust. At first, it may seem like there are only a few bright stars scattered across a huge black canvas. But while your vision insists that the darkness is empty, physics tells us a very different story. That blackness above you is not blank. It should be noted that in every direction, ancient microwaves from the Big Bang are washing through you, the stretched afterglow of a once blindingly bright, hot universe. Between the visible stars, the light from distant galaxies has been pulled into infrared and microwave wavelengths by the expansion of space itself. We do not see it with our eyes, but our telescopes and our data reveal that the sky is quietly blazing. So the next time you look up, try to imagine it as an invisible deep field image. Every tiny patch of nothing is a portal to billions of years of cosmic history, to galaxies whose light left before Earth was even a planet. This means the darkness overhead is not just poetic, it is one of the simplest, most accessible pieces of evidence for the Big Bang that you can personally witness. No particle accelerator required, just you, the night, and a little patience. Pattern interrupt for your brain. What if you could change your eyes? If you could suddenly see in microwaves, the whole sky would glow with the 2.7-degree cosmic microwave background. In infrared, you would watch cold dust clouds and hidden stars swirl inside our own galaxy. In X-rays, the calm night would erupt with violent systems, black holes feeding, and dead stars flaring back to life. In the hunt for alien life, these invisible bands are not decoration. They are how we track atmospheres, temperatures, and sometimes even potential habitability. So, it's time to find out the truth about your own curiosity. If our eyes miss so much of the universe, what else is still hidden from us? In wavelengths, in scales, in phenomena we have not yet learned to see. Tell us in the comments, if you could choose one, supervision, infrared, X-ray, or microwave, which would you pick and why? Optimistically speaking, this is only the beginning. In upcoming videos, we will explore other everyday cosmic clues, why the night is quiet, why the moon's face looks the way it does, and how ordinary sights can encode deep physics and cosmology. If you want to keep unpacking big questions, like why space is so dark, remember to like this video, subscribe, and turn on notifications. Share it with someone who has ever looked up at the night sky and wondered what might be hiding in the dark.